Thank you. So I'll be presenting a longer title here, more descriptive, and the environmental assessment of alternatives to fossil-based mulching plastics and peat substrate in greenhouse tomatoes. So to conduct an LCA, we need to define what's called the goal and scope of the study. Part of this is outlined here, where the goal is to assess the environmental impacts of greenhouse tomatoes using different types of seedling substrate and mulching materials. We also define what's called the functional unit. It's a measure of the function of the study system, and it provides a reference to which all the inputs and outputs and the final results can be referenced to. So in this case, the function is to produce organic cherry tomatoes, and the unit would be 1 ton. The data for organic cherry tomatoes was provided by Miguel in Almeria, Spain. So to perform the life cycle impact assessment, we use the environment footprint methodology, which is a European specific and recommended by the United Nations Environment Programme. As for the specifications, the tomatoes were grown, as Miguel said, in a steel parallel greenhouse, and we compared two scenarios. One is the reference or contentious scenario, where we used fossil-based plastic mulching and peat substrate. The alternative scenario is a potato starch-based bioplastic mulching supplied by Christina and her team in Poland. And for the substrate, horse manure and green forest waste compost supplied by Rafaela and her team at IRTA. So LCA is a system-based approach, looking at all the upstream and downstream effects of a product throughout its lifetime or for a specified amount of time. In this case, it would be the cropping year of the tomato. So here we have what's called the system boundary of all the processes that we are going to assess in tomato production. So it includes what's called the background system in the light green box and foreground system in the gray box, where the background system comprises all the processes upstream of the agricultural field, such as the production of the plastic film and the resource extraction needed to create the plastic film. So the foreground system comprises of all the activities on the agricultural field, such as the application of the plastic film using machinery. So emissions from both systems are shown by the red arrows as being emitted into the environment, or as we call it, the ecosphere. So using the data from Miguel, Christina, and Rafaela, we created a life cycle inventory, which defines all the inputs and outputs from the system. So listed here are some of the important inputs for cherry tomato production. For the contentious and alternative inputs, we have 5.4 meters cubed per hectare of peat or compost, as you can see in the bold here in the third row. So we assumed that they had similar density, quality, and quantity, and that's why the amount is the same. And 194 kilograms of LDPE mulching is needed per hectare, or 186 kilograms of bioplastic per hectare. We included solarization of the ground using LDPE, but possibly bioplastic could be used for this pending investigation. Here we have the emission outputs from the foreground system, where the important emissions come from fertilizer and plant protection product application, such as copper and sulfur. So using that inventory, we were able to estimate results, which I will present on the next few slides. So here we have the results for just the mulching scenarios. So the fossil-based plastic mulching scenario, or CONT, C-O-N-T, and the alternative bioplastic mulching scenario, or ALT, A-L-T, in greenhouse tomato production. So we maintain that peat was the control substrate in both scenarios. The impact categories we assessed, or sometimes I may refer to them as just categories, include climate change potential, land use potential, ozone depletion, acidification, freshwater and marine eutrophication, freshwater ecotoxicity, and fossil-based resource depletion potential. So as you can see here, there's no clear winner in terms of environmental performance, where the alternative scenario performs better in land use potential, ozone depletion, and fossil-based resource depletion, as you can see by the lower number. but may perform worse or similar to the contentious scenario in climate change, acidification, eutrophication, and freshwater ecotoxicity. So an important parameter that we encountered was that the thickness of the bioplastic can influence the results. So Christina and her team produced a film of 40 micrometers or 25 micrometers of thickness, in which we use the 25 micrometers in this assessment, whereas the fossil-based plastic mulching is usually about 12 micrometers. So possibly if the thickness was reduced, maybe also the impacts could be reduced. A hotspot in the bioplastic production was the manufacturing of the starch feedstock. So especially the potato production to create that starch. So we found that the potato production contributes across all categories in the bioplastic production due to the mineral fertilizer use. So if potatoes came from organic farms or the starch was sourced from potato processing waste flows from cutting potatoes, this impact could change. So here we have the results for the substrate scenario. So only looking at changing the substrate. So the peat would be the contentious and compost would be the alternative scenario, but maintaining that LDPE or the plastic, fossil-based plastic was the control mulch. So again, there's no clear winner. The alternative scenario performs better in some categories, but the same or worse in other categories, similar to the categories in the previous slide. So the hotspots in compost production we found were the transport of the forest residues and diesel consumption, as well as the emissions from compost production. So, however, there is a limitation in the compost production emissions. The emissions during compost production were estimated using default factors common for any type of material compost using the environment footprint methodology. Thus, the results may change if we used more adjusted values. We also created a scenario where we substitute both the peat and the plastic, or the CONT scenario, with the bioplastic and compost, or the ALT scenario. And the results, again, as you can see, were not unifocal, where the ALT performs better in some and the contentious performs better in others. So to aid decisions on which system can perform better, we usually normalize the results per EU capita and weight the categories by importance using weighting factors from the environment footprint methodology. So this results in a final environmental performance score, which aggregates all category results into one common unit. So we found that in the graph at the bottom, that the alternative and contentious scenarios were along the same magnitude, with the alternative scenario being slightly lower. So here we have what's called the contribution analysis of each process in the contentious scenario. As seen in the legend on the right, we have all the processes in the production of tomatoes. This is one way to see what the hotspots are in the system as a whole by looking at how much they contribute to each category. So the major hotspots include the greenhouse structure in blue. As you can see, it especially steel production, which contributes across all categories. Also, we have PPP, which is plant protection products, and fertilizer application emissions in purple. So mainly due to the copper ecotoxicity that's applied copper oxychloride. So since the greenhouse dominates across all the impacts, it's difficult to see the impact of the other processes. Thus, we created a scenario excluding it on the next slide. Here, removing the blue, the greenhouse scenario, we can see that machinery in teal and fertilizer production in dark pink are other important hotspots in the contentious scenario because they contribute to things like eutrophication. Machinery, you can see it contributes to across many different categories: climate change, ozone depletion, resource minerals, and metal depletion. In regards to the impacts of the LDPE mulching and peat substrate, which are seen here, they also contribute to many categories as you can see in the pink, the mulching, the LDPE, it contributes to a lot to the climate change, freshwater eutrophication, resource and mineral metals depletion, fossil resource use depletion, which is to do with energy, and peat can contribute quite a lot to land use, fossil use, and climate change. So to show you different types of results, here we have results for the alternative scenario, so with bioplastic and compost. So we again normalize them into per EU capita and weighed the categories by importance to get a final performance score. So this graph shows how much each category contributes to that score, and thus how important and relevant that category is for the system. So here we can see that freshwater ecotoxicity contributes the most due to the copper oxychloride plant protection product use, which is one of the contentious inputs being studied in Organic Plus, as well as the mineral and metal resource use due to potassium sulfate fertilizer. So some important conclusions, improvements, and limitations that we found were that the source of the starch for the bioplastic, where the bioplastic starch came from, was really important. So if it was sourced from organic farms or residual starch from potato processing, it may reduce the overall impacts. We also found the thickness of the bioplastic film also had a large influence on results. So the question is if we can reduce it even more lower than 25 micrometers, because we saw that 40 micrometers and 25 micrometers, the difference between those two was about 37% reduction in overall impacts. We also used general emission factors for compost and bioplastic degradation, which can be improved if we had composition values or adjusted factors. For example, what Rafaela has seen so far is that the ammonia emissions could be lowered as the compost does not have ammoniacal N, whereas the default values we used had ammonia. And the fact that the nitrogen is released very slowly, which can reduce nitrous oxide and nitrate emissions. So we would benefit from having adjusted factors. We also made the assumption that peat and compost had similar quality and density. So the question is, if the same amount of each is truly needed to have the same density, do you need the same amount? And two important limitations in life cycle assessment is that impacts related to microplastics and plastic pollution are not yet modeled, thus excluding possible impacts of toxicity and impacts on ecosystem services. This is currently being studied by many groups, LCA groups around the world. So biodiversity impacts were also not estimated here, in which peat harvest could have high impacts, but this will form part of my PhD research. So that's the end of my presentation. Just wanted to thank Christina, Miguel, and Rafaela for their help and their data. So I can address any questions, or if we have time. Yes.
Thank you.